Hello everyone. Let me start with a thought from real life. When you drive a car, your speed tells you how fast you're going. That's like the first derivative. But when you press the accelerator or brake, your speed changes, and that change of speed is captured by the second derivative. In mathematics, the first derivative dy by dx gives us the slope of the tangent or the rate of change of y with respect to x. But sometimes, we need to go deeper and ask, how does this slope itself change? That's when we use the second order derivative, written as d squared y by dx squared. It helps us study curvature, concavity, and turning points of graphs. Positive second derivative means the curve bends upward, while a negative second derivative means it bends downward. Now let's define it properly. If y equals f of x, the first derivative is f dash of x, which equals dy by dx. Differentiating again, we get the second derivative f double dash of x, which equals d squared y by dx squared. Formula: f double dash of x equals d by dx of dy by dx. This means the second derivative tells us how the slope is changing with x. Let's take an example. Suppose y equals x cubed. Then the first derivative dy by dx equals 3x squared. Differentiating again, we get d squared y by dx squared equals 6x. So the slope is not constant, it changes at a rate of 6 times x. We can continue this process to find higher order derivatives. After the second derivative comes the third derivative, the fourth, and so on. In general, the nth derivative is written as d raised to the power ny by dx raised to the power n, or simply f to the power n in brackets x. For some functions, these higher derivatives follow beautiful patterns. For example, if y equals e raised to the power x, then the first derivative is e to the power x. The second derivative is also e to the power x, and in fact, all higher order derivatives remain the same. Higher derivatives become very important in topics like Taylor series expansions and in modeling motion in physics. Let's now explore the geometry behind the second derivative. The sign of d squared y by dx squared tells us the concavity of the curve. If d squared y by dx squared is greater than 0, the curve is concave upward, like a smiling face. If d squared y by dx squared is less than 0, the curve is concave downward, like a frown. The points where the second derivative changes sign are called points of inflection, where the curve changes from bending upward to downward or vice versa. For example, the graph of y equals x cubed has a point of inflection at x equals 0 because the concavity changes there. Second derivatives also have a direct role in physics. Suppose y represents displacement with respect to time t. Then dy by dt is velocity and d squared y by dt squared is acceleration. That means the second derivative is nothing but the rate of change of velocity. For example, if s of t equals t cubed, then velocity v of t equals 3t squared and acceleration of t equals 6t. This clearly shows how the second derivative is linked with acceleration in motion. So, second derivatives are not only abstract calculus concepts, they are applied every time we study movement in real life. Let's work out an example together. Suppose y equals x squared multiplied by e raised to the power x. Step 1. First derivative dy by dx. Using product rule, dy by dx equals derivative of x squared times e to the power x plus x squared times derivative of e to the power x. That gives to x e to the power x plus x squared e to the power x. Step 2. Now differentiate again. Differentiating to x e to the power x gives to e to the power x plus to x e to the power x. Differentiating x squared e to the power x gives to x e to the power x plus x squared e to the power x. Step 3. Combine all terms. We get d squared y by dx squared equals e to the power x times bracket x squared plus 4x plus 2 bracket close. This example shows how the product rule is often used again when calculating second derivatives. Let's take a moment to recap today's discussion. We started with the idea that the second derivative measures the rate of change of the slope of a function. We then defined it formally as d squared y by dx squared. We saw how higher derivatives can be calculated and how they reveal deeper patterns in functions. Geometrically, we learned that the second derivative determines concavity and points of inflection. In physics, we connected it to motion, where it represents acceleration. Finally, we solved an example to see the method in action. And that's the foundation of second-order derivatives, a key tool in calculus that deepens our understanding of curves, motion, and optimization. In our next lesson, we'll see how these derivatives help in identifying maxima, minima, and curve sketching.